All right, well, now we're in section 7.3, and we are now looking at what are called separable equations. So um, let me give you a moment to copy this example down, and then I'll talk to you about what we're going to be doing here in section 7.3. Okay. Okay, so okay, so let's see here. All right, 7.3, separable equations. What are these? So in section 7.1 and 7.2, 7.1, you were introduced to differential equations. 7.2, you were introduced to direction fields for differential equations, and also using Euler's method to approximate values of a solution to a differential equation, which is important because not all differential equations can be solved. You can't find a solution for every differential equation. I mean an explicit solution. Well, in 7.3, we deal with what are called separable equations. And separable equations are differential equations that, for the most part, we can find solutions to. So what we have here is we have an initial value problem. Okay, we have this initial value problem, and the initial value problem is y prime equals x squared over y squared, where y is 0 equals 2. That's your initial condition. And I note that we can write this differential equation also. We can write it as dy dx equals x squared over y squared. Okay, so when we have a separable differential equation, to solve it, we often want to take the differential equation and write it in the Leibniz notation dy dx. So let's go ahead to the next page and let me show you how we would solve this differential equation. Okay, let's take a look here. So we're going to do what's called separating the variables. We're going to do what's called separating the variables. So what I do, first of all, is y prime on the left side, I express it as dy dx. Now, we have dy dx equals x squared divided by y squared. And how many variables are there? How many variables are there in that differential equation? dy dx equals x squared over y squared. How many variables do you see? There are two. There are two, Jonathan. We have variable x and variable y. And if we're trying to solve this, okay, we're trying to figure out what y equals. So this means then that x is your independent variable and y is your dependent variable. Now what we want to do is we want to rewrite this differential equation so that any terms with y variable in are on one side and any terms with the x variable are on the other side. Okay, that's what we want to do. That's called separating the variables. So, okay, traditionally, I like to have my y variable terms on the left side of the equation and my x variable terms on the right side of the equation. So what I'm going to do here is I'm going to multiply through the differential equation by x squared. Okay, and of course, by doing so, we get some simplification here. I don't want the bold to take up too much space here, but we get some simplification. So the y squared simplify out, and we're left with y squared dy dx equals x squared. But what I can do on both sides here, okay, is I can multiply, okay, both sides by dx. And that's going to cause the dx terms to simplify on the left side, to cancel out. Right? That's what they'll do. They'll just simply cancel out. And then this is going to leave us, we're rewriting the differential equation as y squared times dy equals x squared times dx. Now again, I want to solve for y. I want to solve for y. I want to know what the solution is. I want to know what the explicit solution is to this differential equation. So if I were to integrate on the left side of the differential equation, it makes sense then I would have to integrate on the right side of the differential equation. It is an equation. So what I do to one side of the equation, I have to do to the other side. So I'm going to integrate on the left side, and I'm going to integrate on the right side. So what happens is, well, the antiderivative of, well, first of all, are there any questions so far up to this step right here?
So, Professor, the goal is like to get dy like and the y separate and the x and dx separate, right? So we can then integrate
That's
them.
exactly right. We call this separating the variables.
Oh, okay.
The y variable terms are on one side of the equation. The x variable terms are on the other side of the equation.
Okay.
And you see, what we can do now is we can integrate both sides. Once we separate the variables, you know, now here at this step, the variables are separated. Okay, the variables are separated. Once the variables are separated, well, we can then try to solve for y, find out what the solution is. So we're going to integrate both sides of that differential equation, and these are indefinite integrals. So like the antiderivative of y squared with respect to y is y cubed over 3 plus c1, some constant of integration. Similarly, on the right side, the antiderivative of x squared with respect to x is x cubed over 3 plus some constant of integration, which I'll call c2. Well, I can combine those constants of integration. If I subtract c1 from both sides of the differential equation, I'll end up getting y cubed over 3 equals x cubed over 3 plus c2 minus c1. Okay, so certainly that's true. And c2 minus c1, what I'll do is I'll just call that constant c3. I'll call that constant c3. So I every time I when I combine constants, I get new constants. I just rename them. Okay, I rename them. So like you can't call this C and this constant C. You can't give them the same names because you have to allow them to be different constants. Okay. Now we're not done yet. We're trying to solve for y. We want to know what y equals. So we're trying to solve for y. Are there any questions before I go to the next page? All right, let's go to the next page. So here we are. Here we are. We have y cubed over 3 equals x cubed over 3 plus c3. That's what we have. And I want to get the y by itself. I want to get the y by itself. So what I'm going to do, what we'll do is we'll do some algebra. We'll do some algebra here. So I'll multiply both sides of this equation by 3. And let me see here. Sorry, one moment. Well, and I'll get to that. I'll get to that, what that k is. Good question. Good question. So the 3 distributes on both of those terms, meaning on the right side, I have x cubed plus 3 times c3. On the left side, I have y cubed. Now, again, 3 times that constant c3, well, that's yet a new constant. That's an arbitrary letter. That's an arbitrary letter. So 3c3, I could have called it like C. I don't have to call it K, but I'm just calling it big K. So I'm not going to do like, C4. I could call it C4. But I know at this point that that basically I'm not going to need to do much more in terms of modifying the constants. So, kind of at the end, I'll just put a big K there for that constant. And of course, if y cubed, since y cubed equals x cubed to the plus k, well, I can take both sides of this equation and raise it to the 3rd power. That'll give me then, y cubed raised to the 1/3 power is the same as y raised to the power 3 times a third, which equals y to the first. And so that gets me y on the left side. And then on the right side, I have the cube root of x cubed plus k. Now, this is what we call here, this is a family of solutions. Remember, when you solve a differential equation, if you don't specify an initial condition, you get a general solution. You get a family of solutions. Now what we're going to do, though, is we are going to put in our initial condition, because this is what's called an initial value problem. It consists of a differential equation and it consists of an initial condition. That's called an initial value problem. The initial condition. Well, first, are there any questions up to here? All right. Well, now let's put in our initial condition that y of 0 equals 2. This means when x equals 0, y equals 2. That's what it means. So you see, for y, I put in 2, and for x, I put in 0 in my solution here, in my general solution. And that allows me to solve for k. And I'll get k, well, 2 will equal the cube root of k, but then that means k has to equal 8. Okay, that's what k would have to equal, because the cube root of 8 is 2. Another thing you could do, 2 is k to the 1/3 power. So if you raise let me just hold on. Let me do this again. I mean, here 2 is equal to k to the 1/3 power. So if you raise both sides to the 3rd power, you'll get 8 equals k to the 1st power, because you multiply the exponents. And so k equals 8. And now you know that the solution to the initial value problem, okay, the solution, maybe I can write it here. The solution to the initial value problem okay, and okay, what is that initial value problem? Well, you wrote it down. Y prime equals x squared over y squared, where y of 0 is equal to 2. That solution is going to have to equal y equals the cube root of x cubed plus 8. Okay, and initial value problem, well, I'll underline it. Initial value problem we'll call IVP. How many have heard of MVP, most valuable player? How many have heard of that term, the MVP? Although I think all the players are important. Daniel knows what I'm talking about. Sure, Franklin knows what I'm talking about. Well, this is the IVP, the initial value problem. So, are there any questions before I go to the next page? Okay, I'll go to the next page. And what I have here, this example is actually example 1 out of the book. But I think what I'll do, there's a figure 1 in the book that shows the family of solutions, and I think I'm gonna just go to the book here. So you have this already. You have this. Let me like follow up in the book here with that figure. One moment. Let me get in there. Let me find it here. Sorry, class. Have to get to 7.3. Yeah, this is it. 7.3. Solving a separable equation. So we went through the steps. And we got our, it's really part B that we're looking at. The solution, find the solution where the initial condition is y of 0 equals 2. That's really what we're doing. So again, the general solution is y equals the cubed root of x cubed plus k. But if we put in the initial condition, we get the specific solution, y equals the cubed root of x cubed plus 8. And if we look at the picture here, figure 1, what they've done is it shows graphs of members of the family of solutions. So the family of solutions is y equals the cubed root of x cubed plus k. And for different values of k, you're going to get different solutions. Now, the solution that passes through the point 0, 2 is the solution in red in figure 1. So the solution to the initial value problem, which was the initial value was when x equals 0, y equals 2. That means that solution passes through the coordinate 0, 2, which you can see in figure 1, the red graph does, and the red solution. And that solution would have equation y equals the cube root of x plus 8. Are there any questions on that? Any questions on this problem? All right, I'll tell you what, let's look at another one real quick here. Let's look at another one. Okay, I want to look at example 3. Okay, I want to look at example 3. Forgive me, I just gotta. Okay, so solve the differential equation y prime equals x squared times y. So you see what you do, you separate the variables. So first of all, y prime you write as dy dx, and then you rewrite the differential equation as you see here. So dy over y equals x squared dx, and then you integrate both sides. Well, the antiderivative of y is the natural log of the absolute value of y. The antiderivative of x cubed of x squared is x cubed over 3. And what they do is they just put a plus constant at the end. So, you know, you don't have to go through the steps where you have like I showed you, where you have a constant on each side when you do your integration, and then you combine the constants. It's okay just to mentally combine the constants in your mind and just have a plus C on the right side. Okay. Now, we want to find out what y equals. We're not just interested in the log of the absolute value of y. We want to know what the absolute value of y equals. So what we can do is, well, what can we do? Let me just see here. Hold on. We can write then, we can exponentiate both sides of that equation. So the log of the absolute value of y equals x cubed over 3 plus a constant. If you exponentiate both sides, you'll get the absolute value of y. So the absolute value of y will equal e raised to a constant times e to the x cubed over 3 power. And I know you've seen exponentiation, right? How many have seen that? Because I remember doing that and teaching that in Calculus 1. How many have seen that? Where you exponentiate both sides, all right, of an equation. Sure, Clay has seen that. It's very common, very common. Well, okay, so if the absolute value of y is equal to e to the constant, e to the power of a constant times e to the x cubed over 3, then when we remove the absolute value, y is just going to equal plus or minus that function. That's what y is going to equal. And what we can do is we can take that plus or minus e to the constant and just replace it with a. And so y equals a times e to the power x cubed over 3. It's a family of solutions because a is, you know, that's not determined, you know, and that's your family of solutions. And if you wanted to look at a picture of that, there's like a picture of the family of solutions in figure 4 for example 3. So that's a good example to look at. You'll have on Monday's homework, you'll have a 7.2, which is the Euler's method problems, and then you'll have 7.3, which is separation of variables problems. Now we're going to do more on separation of variables, but with what we've covered today, you're certainly able to do some problems. Yes, question, Clea? Question?
Yeah, so why in this particular case we have plus or minus? Because in the case we did before, we did not do that.
Yeah, so the reason is, it's a good question, So give me just a moment here. If you can stay a moment or two. I mean, this will be in the recording, but I think it's a good question that should be addressed here. So if you have, like, for instance, the absolute of y equals 3, what's y going to equal? Absolute, this is just now an example. Absolute value of y equals 3. Y would equal
3.
Plus or minus 3, right? Because the absolute value of 3 is 3, and the absolute value of negative 3 is 3. So far, so good? So far, so good?
Yep.
Okay, okay. So let's say you had now the absolute value of y equals an apple. What's y going to equal?
Apple, because like we cannot have minus apple.
Plus or minus an apple. The absolute value of an apple is the apple. Absolute value of negative apple is the positive apple. See what I'm doing there?
Yep.
All right, now what we have in this example 3 is y equals plus or minus e to the c. Well, no. What we have in example 3 is the absolute value of y equals e to the c power times e to the x cubed over 3 power. I'm going to treat this whole thing here like my apple. And so y would equal plus or minus the apple. Oh, okay. Plus or minus e to the c times e. I never leave enough room. Hold on.
Oh, I get it. Yeah.
Let me just give myself a little room here. Hold on. It's one nice thing about this new format. It is a little easier to erase things, right?
Yeah. So we have plus or minus because of the absolute value. Okay.
Right. And so y will equal plus or minus e to the c times e to the x cubed over 3.
Yeah.
But that can be thought of as plus or minus e to the c. I can put that in parentheses times e to the x cubed over 3. And so you see, I can replace this plus or minus e to the c. I can replace that with an a.
So in WebAssign we write A.
You could. It'll tell you. I think it'll help. I think it's sort of general. It'll give you some guidance on that.
Okay.
It'll give you some guidance on that. But yeah, that's what's going on.
Thank
Very
you.
good question. You're welcome. Any other good questions, class? Okay, I'll stop the recording.